So in this challenge, we have been given a compiled ELF executable and an encrypted flag file. If we run the program, we see that it requires us to specify an input and output file. Then it does some sort of obfuscation on the input contents and stores the result in the output file. So from this information, I assume that the author used this program to obfuscate the flag into this encrypted format, and our goal is to reverse engineer this program to understand how that obfuscation takes place and try to get back the original flag content. Now, most of the time, static analysis is sufficient to understand the program logic, but here static analysis was nearly impossible for me because this is written in C++ and I have very less experience in that field. On top of that, it's a stripped binary, which means all the debugging info has been removed. So what I did here was I set breakpoints at these function calls and dumped the memory before and after the call to understand how things are changing. Based on that information, I get a rudimentary understanding of what a function does and whether it's worth looking into or not. So after some debugging, here's what I think it does. It calls times 0 and stores the result in this variable. Then it creates a pointer to the source file name and the destination file name. After that, it goes on to read the source file contents into this variable. Now, the main obfuscation logic is divided in two parts. The first part initializes buffer 1 by taking the unique timestamp, and the second part utilizes buffer 1 and the source file contents to generate buffer 2. This buffer 2 is the final result, which is then written into the output file. So let's have a look at what is happening in the first part. First of all, we write n integers from 0 to n into buffer 1. After that, we iterate from 0 to n again and pick a random number in this range. The timestamp is used as the seed for the random numbers. That random number is then swapped with the ith index, and this process goes on. So essentially, this is just a fancy way to come up with a random permutation of n integers, where n is the length of the file contents. This is also why if you run the program multiple times, even with the same input, you will always get a different output. Okay, let's see how this is utilized in the second part. We again iterate from 0 to n and read the ith integer in this buffer. That value is then XORed with the ith character of the file contents. That result is passed as an argument into a fancy math equation, and the result is typecasted into the least significant byte, which is later stored in buffer 2. Finally, the buffer 2 is then written into the output file. But something strange you can notice here is that the timestamp is also being passed to the write function. Why would that be needed? Upon inspecting the code, it seems that the timestamp is also being printed after the obfuscated file contents. You can actually verify this by taking a sample input. Here, the source file has 11 characters, but the output resulted in 15, which is exactly 4 more than 11. Those 4 bytes are the unique timestamp. And having this leak is very critical because now we have the exact same timestamp as the author. And since this timestamp was likely used as a seed for the random numbers, having this seed leak is equivalent to having all the random numbers leaked. Also, since the length of the encrypted flag is 46, so this means that the actual flag length must be 42. Now, if we patch the program to use this specific seed and let it continue, we will be able to dump the exact random permutation. After some cleaning and formatting, this is how it looks. Now what happens is the actual flag bytes are XORed with these corresponding integers and the result is fed into the math equation, and that result is being written into the encrypted flag file. Now think about this, the flag comprises of only printable ASCII characters, so every character only has 95 possibilities. Even if we brute force every character, we would need roughly around 4000 computations, which is very trivial for any modern computer. So this is exactly what I did. I brute forced every character to find the one which satisfies this equation, and that is how I was able to get the flag. Very fun challenge and very fun CTF overall, which is also why I am proud to say that this year my team ResetSec has secured the 5th rank.